Good morning, everybody. So the purpose of this presentation is to give you some more accurate data with the heat transfer coefficient. Until now, the heat transfer coefficient were very often a constant value in the softwares, and so now the idea is to find the good heat transfer coefficient depending on the product that we will use. The quenching fluid that we will use. So first we'll speak about the different quenching media that we have on the marketplace, because the first is to understand what you use as a customer for quenching fluids. And then Stéphane will present how he model all this fluid in Forge. And we will speak about a case study. Just at a glance, who is Houghton? Quaker Houghton is the worldwide leader for heat treatment product. So we have something like $55 million in the world in all significant industry company, and $19 million in Europe. So just for heat treatment, it means something like 700 customers in Europe. Quaker Houghton has a complete and innovative range of products, and I highlight innovative because our goal is not to propose something equivalent to some other product from the market, but is to give something with value added, like health and safety, like performance with more productivity, or with cost savings. Quaker Houghton has aerospace approval for oils and polymer, and we were the first to create oils and polymers. We developed first this type of quenching media in the previous century. And in terms of support, because we know it's very important to have a strong support, we have 7 heat treatment laboratories all over Europe. 8 product managers specialized in heat treatment, and 1 center of excellence in Barcelona with 2 R&D developers. So we will speak about different quenching media. Yesterday we had some red-white quenching, but today it will be not as fun quenchant. It would be oil and polymers. So in terms of market, oils represent something like 60% of the market. And in this 60%, we can say that we have about 60% of cold quenching oil. Cold quenching oil means we use them below 80 degrees, between, I would say, 20 until 80 degrees. So it's mainly for fasteners, screw, U-bolts, forging parts. We have then a second part, which is called warm quenching oil, used between 80 and 120 degrees. It's something like 20% of the market for oils. It's very often used for bearings, parts which have a risk of distortions. And the last one is hot quenching oil, used at more than 100 degrees until 180 degrees sometimes. It's mainly for gears when the risk of distortion is very high. The second part of the quenching fluid are polymers. Of course, we developed polymers because of advantage with fire resistance. We don't have a risk of fire with polymers because it contains, depending on the product, a dilution with 90 to 80% of water in use, so no risk of fire. In this polymer, we have 2 types of process. The first one is induction hardening, which is often used with polyalkylene glycol. It represents 30% of the market. It's very often used for tulips, shafts, crankshafts. And we have what we call mass quenching. So it can be done with either PAG, polyalkylene glycol, or polyvinyl pyridine, which is what we call the oil-like quenching speed. So we often use it for railways, semi-finished parts, bars, gas cylinders, wind turbine rings, and some of those type of parts. And then we have a last category, which is polymer for aluminum. There's more and more aluminum quenched. We know that very often it's used with water, it's quenched with water, but we have some specific product which helps to reduce distortion. We spoke about late weighting for the aluminum for all parts, and having small parts, thin parts means high distortion, and trying to quench with polymer helps to reduce distortions. And so the last one is salts and things like that. Of course, I don't speak about water, which is not really something very known from us. So how do we proceed? We measured, in fact, the cooling speed with the system which is called Smart Quench. So we have a probe which is heated at 870 degrees. And then inside this probe, we have a thermocouple. And we will quench this probe into the fluid that we want to test. We have a beaker for oils. And so we will have a fully automatic system to transfer the probe into the fluid in order to avoid any manual differences. And for polymers, it's done with agitation, so we have a special equipment, a special device with a propeller turning at 1,500 rounds per minute, giving a speed at something like 0.6 meters per second for polyvinyl pyridine. So this gives a temperature with the time, and the derivative of this cooling curve gives this line, which is the cooling speed, the cooling rate of the fluid. And that will be the base of our study with Transvalor, and that's based on this cooling curve that we will use the calculation of this inside the software. The very important parameter that we use is the maximum cooling speed that we can see there. We have said that it's very important to find a good quenching fluid, but it's very important to understand that depending on the way we use it, we can have very, very significant difference in terms of cooling speed and then in terms of heat transfer coefficient. And we show for oils that having 10 degrees difference in terms of temperature of the oil, initial temperature, would give more or less 1 degree per second more in cooling rate. So it's at the maximum when we speak about the current range of usage, which is for an oil, cold quenching oil between 30 and 80 degrees, something like 5%. So it's not very, very significant. Having 5 degrees or 10 degrees more is not so significant for oils. The same with agitation. We used our database with all the quenching oil that we had, and based on all this database, we can say that the agitation, when the agitation changed from 0.1 meters per second, we can say that it gives a difference in cooling speed by 1 degree per second, which at last it's not a big evolution, a big difference. So that's why we know that sometimes there's not a big agitation, or even sometimes no agitation inside the quenching bath. And the last one is the oil speed. We have a very wide range of speed of the oil, depending on what we want. So the speed without any accelerators is something like 45 degrees per second. But with the experience that we have different type of accelerant which help to achieve very high speed. We can have something like 110 degrees per second with the additive that we use in our formulations. So at the end, we can say that for oils, what is really important is the oil speed and to monitor properly these parameters. For polymers, it's different. The temperature is something very important, and having 5 degrees of change in the initial temperature would at last give 8 degrees per second modification in the maximum cooling speed. So in the current range of usage for the temperature of a polymer, which could be between 20 and 50 degrees, we can have a maximum of difference in cooling rate by 50%. So that means that we really need to pay attention to the temperature when we use a polymer. With agitation, when we speak about immersion tank, we know that agitation from polymer is something very key. And having a difference in agitation by 0.1 meter per second gives 2.5 degrees per second in terms of difference of cooling rate. And sometimes we can have some bath with 0.1 meter per second until 1 meter or 1.5 meter per second. So it's very important to consider this parameter agitation because it can really make a big change in terms of cooling speed. Oops, sorry. And the last one, concentration. 2% of concentration, depending first on the product that we have chosen, but then with the concentration, 2% will give more or less 8 degrees C per second of change in the cooling speed. So we can have a high difference on cooling speed if we don't manage properly the concentration. So we have seen that for oils, it's very important to control the maximum speed of the initial oil that we use, but the agitation and temperature is not so important. But for polymers, temperature, agitation, and concentration need to be controlled properly to be sure that the heat transfer coefficient will remain the good one. So it's based on this information that we have worked with Transvalor in order to model each group of products, so polyalkylene glycol, polyvinyl pyrrolidone, oils, low-speed oil, high-speed oil, hot quenching oil, and so we have simulate all the evolution of these parameters to give you a general overview about what could be your heat transfer coefficient depending on what you use. And the second point is to model some new generation of innovative Quaker Houghton products. We know the chemistry is changing a lot. For the moment, we've reached, you probably heard about that. And so the idea is to propose something for the future. And we created a special range of synthetic high-performance oil. And the goal was to implement in the forge all these new products to be sure that with the concentration, with the temperature, or with the agitation, you will have exactly the same heat transfer coefficient inside your software. So I will let Stéphane explain how he managed this.
Thank you, Mickaël. So, hello everyone. Okay. So, okay. Okay. So I will show you how we took all this knowledge from Quaker Houghton to model these fluids in Forge. So a brief introduction by reminding you how we take into account the ambient media in Forge. So we use the Newton heat flux law, which is quite simple. The heat flux is proportional to the difference of temperature between the surface and the surface of the billet and the ambient media. So here. And the coefficient of proportionality is the so-called heat transfer coefficient. So the more accurate we are to describe this coefficient, and the more accurate we are to describe our liquid. So a first step, which is really common in Forge, for example, is to have different constant values for different quenching media. But if we look at what happens during the quenching of hot billet, we see three phenomena at the surface. First, at high temperature, we have a vapor film which reduces the exchange at the surface. Then at intermediate temperature, we have a strong convection and the exchange increases drastically. And finally, at a low temperature, exchange reduces once again. So usually what we do is that we decide that the heat transfer coefficient is not constant, but is a function of the surface temperature. And such difference of description may have a big impact on your simulation results. So let's consider the quenching of a cylindrical Inconel billet into commercial oil. So this is the classic smart quench characterization, which is used as the main way to determine quenching fluid's properties. So the thermocouple here at the center of the probe gives us a cooling curve. And now, if I use Forge to reproduce this simple experiment, and I use the optimization module to determine the best heat transfer coefficient. If I consider a heat transfer coefficient which is constant, we can see here the simulated curve in light blue. It follows the general trend, but it is not perfectly accurate. And if we consider a simple description which is function of the surface temperature, it is clearly easier to have an accurate result. So we see here two things. First, that we need some description function of the surface temperature to have accurate results. And second, we need first one characterization, experimental characterization, and an optimization procedure. So you saw before the characterization part, I will slightly detail the optimization procedure. So the idea is to first reproduce the smart quench characterization. So a very particular probe is used. So we reproduced it. And to reduce computation costs, we made sure we simplified the geometry while making sure that the results are the same. And then we considered an optimization procedures, which is based on finding a heat transfer coefficient curve, which is defined by 5 points, which three of them are mobile in temperature and heat transfer values. So that way we are able to replicate the phenomena happening at the surface while having reasonable computation cost. So an example here, I use as an input data the cooling curve that you see here. Then the optimization is launched, and various solutions are classified by the cost function, which is simply a scalar that determines the difference between the experimental result and the simulation result. And for the best result, we have one heat transfer coefficient curve and a good fit between the simulation and the experimental data. So doing so for many quenchant, here it was a octoquench C105, but doing so for many Quaker Houghton quenchant, we were able to do a database. So this database is right now available in the last version of Forge, Next 3.0. It has 68 Quaker Houghton quenchant, which are classified by their composition, their temperature, their agitation, and their concentration, the main parameters as you saw before. Okay, to have access to the desired Quaker Houghton quenchant, you go into the Workbench store, heat transfer, Houghton quenchant. Then you have a list of the various quenchant available. And by selecting one of the quenchant, description appear, which details the different important aspects, which are the heat transfer coefficient curve and the fit between experimental data and simulation results. So here an example, some heat transfer coefficient curve, here for polyalkylene glycol polymer solution. And you can see here that the higher the concentration, the lower will be the heat transfer coefficient curve. So it has some links to what Mickaël said before, of course. And as you can see, each time we had a good fit between simulation results and experimental data. Okay, I will pass this one, but that's the same aspect. So to briefly conclude, I will say that this work can be described here by these two graphs with using the Quaker Houghton quenchant. You can use the database directly and you will have accurate results during your quenching simulation. And one other aspect that we want to detail here is that maybe you can use this quenching database differently in order to adjust your quenching processes. For example, replace oil bath by a polymer solution. So that's what we will discuss in the case study. So, okay. So the idea here is to show you an original yet very practical way to use this database. So here a brief introduction. Today, Quaker Houghton and its clients have more and more constraints to change oil bath solution to cleaner solution due to environmental reasons imposed by norms, for example, sanitary reasons for people working into the plant and people living next to the plant, and of course, economical reasons. And while respecting these new norms, the new fluid must also respect at least similar behavior than the previous and initial oil solution. So do we have the same microstructure after quenching? Will we have same level of residual stresses and distortion? So how do we do to find the optimal alternative solution? So first thing, which is quite qualitative, is to compare what we have at the beginning, which are the drasticity curves. So let's consider a classic commercial oil from Quaker Houghton, which is the octoquench C1804, and which is used by Quaker Houghton customers for bearing rings, for example. So we have such drasticity curves, and we will compare this drasticity curve with 3 polymer quenchant candidates. So here we consider the 3 here. And if we compare all these drasticity curves, none of the polymer candidate replicates the drasticity curve of the oil quenchant, which is normal because oil and polymer can behave the same way. But at least we can here consider the best candidate out of the 3 polymer candidates, which is the AquaQuench 300, which have at least a similar maximal cooling rate. So with the drasticity curve, we can go further and compare also the cooling curves. And using the optimization procedures, we can compare the heat transfer coefficient curves. So, okay, so here we can see that it's not the same, and here we can't tell if the bearing ring we have the same properties. So that's why we will use Forge to go further. So first of all, this study is a proof of concept, and we decided here to go for local induction heating before the quenching stimulation. So briefly, we can see the heating part. So what's important is that next to the inductor, the temperature increased, which lead to austenitization of the high temperature parts, and which will transform once again during the quenching. Then we will do the quenching simulation with the initial oil solution and the best polymer candidate. And we will also compare these 2 solutions, which are supposed to be quite similar, to 2 extreme quenchants, which are agitated water and slow oil. So here, the quenching times of the initial oil solution and the polymer candidate, what we can see here is that we have really similar quenching time, which is in agreement with the drasticity curve. We can compare this solution with the extreme quenchant. We have 10-second quenching time for agitated water, and more than 2 minutes for slow speed oil. So this will have a big impact on the microstructure. For example, for agitated water, we will have martensite here, only martensite, no benite, which will lead us to homogeneous hardness, but on the other hand, great residual stresses. And oppositely, we will have significant formation of benites with the slow speed oil up to 20%, which lead to heterogeneous and unsatisfactory in-use property in the bearing ring, but lower residual stresses are achieved. So that's why we are interested in intermediate quenching times, and as you can see with the oil solution, we had only a couple of % of benite which appears, which lead to almost homogeneous hardness. And the same can be said for the polymer candidate, where we have up to 4%, so that's more or less the same, and the same hardness too. So here we can see that the residual stresses maps, and we can see here that for the initial oil solution and the polymer candidate, we have more or less the same results, which are intermediate in terms of residual stresses between the really drastic quenchant and the really slow quenchant. So last aspect that we will treat qualitatively, which are the distortion. And to treat it qualitatively, I decided to compare between the different solutions, the plastic energy. And as you can see, the minimum and the maximum of the plastic energy is determined by the 2 extreme quenchants, so the slow speed oil and the agitated water. And you can see here that the initial oil solution and the polymer candidate have really similar values and are located in the lower part of the spectrum. So probably the distortion behaves the same way as this graph. Okay. So to conclude this case study, which was done on a bearing ring, we saw that it is only through simulation that we are able to tell that the bearing ring at the end of the quenching will have the same properties, and in this particular situation we can replace the oil bath solution by the polymer candidate here. What we could imagine to go further is to link these results to some fatigue failure analysis to determine even better quenching fluids and have an even more quantitative approach. Some last word about the Transvalor and Quaker Houghton collaboration. So this is one of the fruits of this collaboration, the Quenching database, which I hope you can use to have better accuracy, and some which you can also use to adjust your processes. This collaboration will continue on this particular subject of the quenching fluids, but will also, it is also existing on other subjects, which are the lubricant and the lubricant properties. This work is done by Patrice Lannes and Franck Bellois. Thank you for your attention.